Okay, so today's lecture we're going to talk about some different types of chemistry, and we're talking about ways of making carbon-carbon bonds. And I'd say these are new ways. Well, they've only started reaching the undergraduate curriculum about 5 or 6 years ago. But they were basically these dates right here, 2010, 2005, are the dates of the Nobel Prizes awarded for these reactions. In 2010, Suzuki, Heck, and Negishi won the Nobel Prize for palladium coupling reactions. We're not going to worry about the Negishi reaction. We're going to talk about the Suzuki and Heck later on. And then in 2005, Alkene Metathesis received the Nobel Prize, and Chauvin from France, he did the theoretical studies showing it was possible. Schrock came up with a catalyst to do the work, but really it was Grubbs that also shared this Nobel Prize. He developed a catalyst that worked much broader sense. Schrock's catalyst was good, but it was very finicky, and he didn't have had something wrong with the system, it would fail. But Grubbs' catalyst worked with a large number of functional groups, and so these reactions, Suzuki, Heck, and the Grubbs catalyst, are what we're going to be talking about today. So let's start off with the Suzuki reaction. The Suzuki reaction takes a boronic acid and a halide, where X is Cl, Br, or I. I works best, Cl works worse. Cl is the cheapest. Br is sort of in between of inexpensive and also working, so a lot of times you'll see this used with a Br. And it uses some palladium catalyst. The catalyst that's used can be quite specific or not specific at all. It could be just random palladium metal. We're not going to have you specify the catalyst, just write PD. Some sort of base. And when you do this reaction, what happens is you cut off the boron, cut off the halogen, and it sticks the two rings together. Now, this works best when the carbon attached to the boron and the carbon attached to the halogen is sp2 hybridized. Now, I want to say this right up front. Even though these carbons are sp2, they don't work. Those are carbonyls. So they can't be it has to be a carbon-carbon double bonded to another carbon. Can't be to an oxygen or to a nitrogen. The pi bond has to be to another carbon in these reactions for the Suzuki and the Heck reactions. And it can be used for a wide variety of functional groups. Can be used. And say if you had a carbonyl here, and an OMe here, this would be the product. Okay. So, the mechanism of this reaction. is going to be a different type of mechanism. It's a mechanism that's used more in inorganic chemistry. It's called a catalytic cycle. And it is indeed a palladium catalyst. You might need just one molecule of palladium catalyst for every 10,000 molecules of substrate you have. And what the catalytic cycle is it shows the fate of the catalyst, how it chugs out in producing the product. And so for this, we're going to use some abbreviations. So we are going to abbreviate this reaction, boronic acid plus this halide, palladium and KOH, gives this. Well, we're going to abbreviate this molecule as this, and we're going to abbreviate this molecule this, where AR stands for aromatic ring, not argon. Okay. So, what happens in this reaction is you start with your palladium metal. And your palladium metal interacts with your aryl halide, and the palladium inserts itself between the carbon and the bromine bond. This is what is referred to as oxidative addition. We've had other oxidative additions in the past. One chief example of an oxidative addition is making Grignard reaction, where the Grignard inserts itself, the magnesium inserts itself between the carbon and the magnesium bond. That's another example of an oxidative addition. You go from palladium 0 to what's called palladium 2. Both carbon and bromine are more electronegative than palladium is, so therefore palladium becomes oxidized. And then what happens next is what's called a ligand exchange. This is where the base comes in. Well, the hydroxide replaces the halogen. Still is palladium 2. Next, comes a step referred to as transmetallation. This is where the boronic acid comes in. Essentially what happens is you're exchanging one metal for another. You're exchanging a bond between the phenyl and the boron to a bond to the phenyl to the palladium. And so now we have 2 carbon groups on there. Now, this transmetallation step think of it as this. The lone pair on the OH off of the palladium coordinates to the boron. What happens here then is this structure, have too many palladiums there, that should be a phenyl. Happens to this structure then is the electrons from the boron phenyl go to the palladium atom, and then the electrons from the palladium oxygen bond go onto the oxygen. Giving this structure here, and borate. This is the transmetallation step. Now, the resulting molecule loses the 2 carbon groups. They end up combining together. Think of it as like that, or you can move the electrons the other direction. Then the net result is you get a bond between those, and that flies away. And now the electrons went onto that palladium 2, changing it back to palladium 0. This is what's called reductive elimination. And there's our product. And you regenerate the palladium catalyst to have another does another oxidative addition with another aryl bromide, and the process repeats itself again and again and again. The Suzuki reaction is used to make a carbon-carbon sigma bond between two sp2 hybridized carbons. And that's a very unique one. And so if you see a sigma bond between 2 sp2 hybridized carbons, that comes from a Suzuki reaction. Now we need to talk about where the boronic acids come from. Well, they come from organolithiums. Or you can use a Grignard, although Grignards are not nearly as effective as boronic acids are. As organolithiums are. But you treat this organolithium or a Grignard with trimethyl borate, followed by H3O plus, to give the boronic acid. The mechanism of this is the carbanion attacks the empty orbital on the boron, which is a p orbital. And then not much else happens until you add the H3O plus. And what the H3O plus does is it protonates one of the OMEs, making it a good leaving group. And leaving group leaves. What that does is that opens up a spot on the boron for water to add. Water takes that proton off. And then you protonate another OME. And then with the boron, with the methanol as a good leaving group, methanol leaves. And what we've done in these steps, going from this molecule here to this molecule here, we've exchanged an OME and an OH. Well, we have one OME left. We just repeat this process. And we get the boronic acid out of it. So, boronic acids come from organolithiums or Grignards. And I said before that the Suzuki reaction is very good at making carbon-carbon single bonds between two sp2 carbons. And when you break this apart, you can break it apart of one of two ways. One carbon gets a boronic acid, the other carbon gets a halogen like a bromine, or the other one. Gets a halogen, the molecule gets boronic acid. Now, either of these reactions work. Just need palladium KOH. But this one is better just because the organolithium necessary to make this boronic acid right here is this organolithium. This is an illegal organolithium because organolithiums in Grignards can have carbonyls present. So it is possible to make a molecule like that. But the thing is, it doesn't come directly from this. It would have to come from this. And so that just adds more step to it. And then this comes from that. And then to go from here, the boronic acid, trimethylborate, THF, just a solvent, THF, H3O plus, and then a catalytic amount of acid and water to remove the protecting group, and then you're there. Then this molecule right here and then it's just a matter of electrophilic aromatic substitution to generate this molecule right here. This one's pretty straightforward. They are paired to each other. There's your orthopara director, so that goes on first. So going on last would be the carbonyl. And then bromine. And then this can be used to convert that right there. Zinc mercury HCl. Or you can also use the Wolff-Kishner conditions. Give to that. And so that's a possibility here. This route up here is better because you don't have to worry about protecting this at all. So, lots of different ways of doing this. Some ways just better than others. Okay, but that's the Suzuki reaction. The Heck reaction. That reaction, it's a way of making alkenes. It's another palladium catalyzed reaction that again uses a chloride, bromide, or iodide. And it really should be an sp2 carbon. And like the Suzuki reaction, it can't be a carbonyl or a double bond to N to make it sp2. It has to be a double bond to another carbon or so. Or an aromatic ring of some sort. So, on this, what you do is you take a halide and you treat it with an alkene, presence of palladium and base, and you get a transalkene. When it comes to the alkene reactivity, ethylene reacts faster than monosubstituted alkenes. Monosubstituted alkenes react much faster than disubstituted. Disubstituted react much faster than trisubstituted. And tetrasubstituted don't react at all because you do need at least one hydrogen on it. And it's a really nifty reaction. That it's a way of easily making alkenes. Now we can use other ways of making alkenes, include the Wittig reaction, but that would take you several steps to make this particular alkene from a Wittig. As opposed to here, pretty straightforward. And here we have the Heck catalytic cycle. And we'll just do it like so, with phenyl bromide and this alkene. You start out with palladium 0. And the first step is just like the Suzuki reaction. The palladium inserts itself between the phenyl and the bromine bond, so the carbon-bromine bond. It's called oxidative addition. And then your alkene comes into play. And this is called ligand association or alkene association. Essentially what it's doing is this palladium atom is sitting on top of the pi bond of the alkene. Now this can be orientated either way, but the R group off of the alkene orientates itself away from the bulky phenyl group. Next comes what's called the ligand insertion reaction, where the electrons from the phenyl, the palladium phenyl bond, go to the end alkene carbon. That forces the pi bond up to form a full bond with the palladium. So sometimes they show this ligand association bond as a dotted line or as just a line. It creates this full bond here. And so what's happened here is the phenyl has just become attached to the CH2. And then these electrons go up, so now the palladium is attached to that carbon right there. If we were to number these carbons, 1, 2, 3, 4, 1, 2, 3, 4. Now, the next step is what's called a beta hydride elimination. Carbon 3 is the alpha carbon. Carbon 4 is the beta carbon. That's a beta hydride. What happens is the electrons from the carbon-hydrogen bond go to the palladium, and then the electrons from the carbon-palladium bond go between the alpha carbon and the beta carbon. And what you end up getting is predominantly the trans-alkene. In this species. And this is where the base comes in. Electrons from the base take this H off. These electrons go here, and the bromine leaves. The electrons are going to the palladium. That makes it a palladium 0. And we're getting rid of water and bromide. This step right here is a reductive elimination step. It's a reductive step because the electrons are going onto the palladium center, going from palladium 2 back to palladium 0, and the process starts over again. That's the Heck catalytic cycle. And it can make very complex molecules rather quickly, such as this molecule right here can be made in 2 steps from benzene. You can make it from the Heck reaction and just use excess bromobenzene in this alkene, palladium KOH, bromine and FeBr3. And so you can see how big of a time saver this is. And that's one of the reasons why it gained a Nobel Prize, because this is just a remarkable achievement. Trying to do this with Vedic chemistry would have taken a very, very long time. Okay. Now, the last reaction I want to talk about is alkene metathesis. And this reaction changed the way we thought about how to make alkenes. And it's hard to put that into perspective at this level, but this really revolutionized the polymer industry, as well as the synthetic industry as well. So essentially, the idea of this alkene metathesis is you take an alkene and you add a catalyst, and what the catalyst does is it breaks apart the alkene at the carbon-carbon pi bond. At the double bond itself, it splits that and then recombines the two molecules. And so if you had two different alkenes, you can end up getting lots of different products. And all sorts of different combinations of them, where you split apart, make these into separate units, and then recombine them. And in fact, you can get a whole mess of this. Chauvin figured out that this was possible and did the computer modeling and the thermodynamic studies on this. Schrock came out with one of the initial catalysts for it, but really it was Grubbs that came out with the catalyst that really worked to do this. Now, to avoid getting a mess, what you have to do is be very careful on your substrates. And so, first of all, let me show you what the Grubbs catalyst is. And the Grubbs catalyst is the following. And then this alkene is attached to some sort of R group, and that's a ruthenium molecule. And sometimes this is abbreviated where CY is the abbreviation for cyclohexyl. Now, this is what's called the generation 1 catalyst. There are other catalysts. The generation 2 catalyst is much, much better than the generation 1 is. It's much more reactive. But we'll just stick with the generation 1 catalyst. And you can abbreviate this further and just have what the important bits are. And that's basically a ruthenium with a bunch of other stuff attached to it, doubly bonded to a carbon. So this you can use as the abbreviation for the Grubbs catalyst. And one way you can use this Grubbs catalyst reaction is what's called a ring closing metathesis. It's a lot like this reaction right here, the alkene metathesis reaction, only it's a little bit more controlled, giving you a clean product. This ring closing metathesis, it's also abbreviated RCM. It's good for making unstrained rings. I should say cycloalkenes. So 5-membered rings or greater. And it can actually be used to make rather large rings. What you do is you take a molecule like this that has 2 alkenes on it, and you chop off the end carbons and create a new bond. In this case, if we were to number this, 1, 2, 3, 4, 5, 6, what you do when you add your Grubbs catalyst is you get this. The byproduct of this reaction is ethylene, and that comes from the 2 ends. The mechanism of this reaction is very similar to the mechanism of the Wittig reaction. where you do a 2+2 cycloaddition. And all these steps are reversible. And that's the key to this reaction. And I'm going to have to number, otherwise I'm going to make a mistake. So you make this 4-membered ring, and then the 4-membered ring splits apart. And I am going to cheat. We know the product is a 6-membered ring. So what I'm going to do is I'm going to go ahead and draw a 6-membered ring. Then I'm going to get rid of the cycloalkene and put an alkene going out here, double bond here, and your other product was made just right here. These 2 carbons came from right there. If we were to number, this is 6, 5, 4, 3, 2, 1. See how it matches that? Just a different conformation. And then you do this 2+2 reaction again. And then you break apart. When you break it apart, you form your product, and you regenerate the Grubbs Catalyst, and that process starts all over again. Okay. So, it's good. Now, a rather neat reaction of the Grubbs Catalyst, besides just making these cycloalkenes, is a reaction called ROMP, which stands for ring opening metathesis polymerization. And I said that this revolutionized the polymer industry, and that's because of this reaction right here. The ring closing metathesis is only good for unstrained rings, mainly because it's a completely reversible reaction. And what's driving the reaction is the formation of this of ethylene, which is a gas that bubbles away. But in a completely reversible reaction, if your product's not stable, it keeps on reacting further. So if you start out with a strained ring, ignore warning. And you add the Grubbs Catalyst to it. What you end up doing is you end up splitting this molecule. And I'm going to actually put our initial Grubbs catalyst having an R group. When you split this molecule up, you end up getting a new Grubbs catalyst. The mechanism of this is the same mechanism. As before. And then this right here finds another norbornene, and it repeats the process. And it finds another norbornene, and another norbornene, and you keep repeating the process, and you get these repeating units. And all the same, you end up with one R group at the end, at the one end, and you end up with a Grubbs catalyst at the other. This is what's referred to as a living polymer, because at the end you have a Grubbs catalyst. So if you run out of norbornene, your Grubbs catalyst is still sitting there at the end of it, and you can add in another norbornene with another trait. So essentially what you are able to do is make what's called a block copolymer. So, what do I mean by that? Let's say we start out with a norbornene that looks like this. We'll call this A. We treat it with a Grubbs catalyst. We end up polymerizing it, then re-ending it. Okay. The length of this chain is depending on the relative concentration of A to the Grubbs catalyst. Then what we can do is throw in B. Let's just say B is just plain old norbornene. Well, then you start incorporating B into the mix. How much B is incorporated in the mix is, again, factor in how much concentration you have. Then you can throw in C into the mix. Let's make C something like this, a cationic compound. Well, when that goes in, you have your A's, you have your B's, then you have your C's, and then you have your Grubbs catalyst. Well, this is what's called a block copolymer, where you have repeating units that are separated in blocks like this. And these block copolymers can have very specific properties. like in this case right here, A are anionic, B are neutral, C are positive. Well, positives are attracted to negatives, so we can have this do some sort of folding. That gets the A's and the C's together like that and get all sorts of shapes at basically at the molecular level, causing all sorts of different properties are possible. Okay, I've ran over time, so we will pick this, actually won't pick this up, we'll start a new set of reactions on Friday.